Hi, my name is Dennis. Welcome to Foundations AWS VPCs, native and hybrid network connectivity. Let's go ahead and get started. Our learning objectives for today is that we want to understand the use case needs of these services like Direct Connect, VPNs or virtual private networks, and then direct API connectivity into our virtual private cloud. We also want to apply VPC peering and endpoint techniques to secure the network connectivity and also potentially save costs in your workloads. Finally, we want to be able to connect to the AWS VPC account by using multiple secure methods and tool sets. Let's get further into our discussion and see how we're going to do that. First of all, VPC fundamentals. VPC stands for Virtual Private Cloud, and it really is just saying an abstraction of virtualized networking in the AWS cloud specifically. Now, you might hear terms like VPC in other cloud environments, such as Google Cloud Platform, or even at Microsoft Azure using VPCs. It's all a generic term to say we're going to contain networking inside of our accounts as a tenant for virtualized networking and other segmentation at layer 3 and above. We want to understand that VPCs are really, again, just virtualized private cloud, but really a virtual private cloud in the form of a network. Now, everything relies on networking to actually traverse the internet. What we see here is that we have a single VPC inside multiple availability zones. We have route tables just like an on-premise network, and we have potential connectivity just like we do with an on-premise network. In fact, let's take a look at how we can have that connectivity. First of all, we have VPNs and other connectivity, just like you would with other on-premise networks. At layer 3, we have routers or virtual private gateways, and then we have routes that go with that, such as the routing tables that you see here, as well as here. And we have multiple subnets within our virtual private cloud. So if you specify 10.0.0.0/16, which is 16 bits for networking and 16 bits for hosts, you can come up with multiple subnets inside public and private subnets for your services inside AWS. Now, some examples include the 10/8, 172.168.0.0/12, and the 192.168.0.0/16, like you have at home. These are called RFC 1918 addresses, or otherwise known as request for comments. Request for comments is usually done by networking engineers and many other experts around the world to determine what our next standards are. For example, RFCs might also include RFC 793, which is the term for TCP connection. So transmission control protocol, everything has an RFC in today's modern technology stack. And so what we're using here is internalized IP address schemes, and then also VPCs with AWS is assigning our WAN IP addresses from the direct pool. Now, as you can see here, we have multiple gateways and multiple routes. You can have a direct connection route, a VPN, or you really don't need a networking at all. Maybe you just want to worry about services being produced out to the internet. All of this is enclosed inside your enclave, inside your account, or multiple accounts as a VPC. Let's dig a little bit further into what that really means for other services besides the general networking concepts. Now, AWS itself has availability zones and regions. So the first thing you need to understand about scalability, and as we scale horizontally, we understand that Amazon Web Services have two distinct premises for sites. We have availability zones, which really means I have a data center. So a data center, remember, is made of one or more buildings that have redundant power and links. But really, if you think of AZ or availability zone, think of data center. Now, these availability zones all have multiple connections in between them for highly fault tolerant and redundant power and network connectivity. And for each region, there are at least 3 zones, 3 availability zones almost in every region. These circular dots that you see here in the Americas represent different regions, and we also have multiple regions across the world. The availability zone is considered a single data center, logically, and then of course regions are a grouping of one or more data centers. So if one availability zone goes down, if you have your site replicated or your workload replicated in the same region and replicate it into a different availability zone, you would still remain up as if nothing happened. Now, let's just say King Kong comes around and says, we're going to destroy an entire zone. You can have multiple region replication going on to have that multiple failover capability in the event of a true disaster. The more redundant that you get, the more resilient your solution is, the more global it's capable of, and with the right architecture, it could also be faster. Now, some examples also include what we have is called regional codes and uh, availability zones and preferences. So, US East 1 is North Virginia, US East 2 is Ohio, and they have availability zones of A, B, and C, respectively. So just know that the more zones you have, the more regions that you have, the more resilient, high availability, and potentially the faster of your global, faster portion and access of your global architecture and structure for your end users. Now let's move on to subnet types. Just like what we learned in network foundations and what is the premise of the stack itself, the stack can include the network underneath, layers of networking requirements underneath. And just like that, you have layer 3 routing like NAT gateways or network address translation. If you want to have what's called a public subnet, you always have an internet gateway attached. Now the internet gateway, let's draw this real quick. The internet gateway is exactly what it sounds like. It is the gateway to and from the internet. So if you want internet access to your VPC, let's say egress, you always have to have an internet gateway. Now, if you don't need internet access for whatever reason in your workload, you don't attach an internet gateway. The internet gateway, from a perspective of cost, is always free and can be attached at your VPC anytime. That is the logical gatekeeper to and from the internet. And we have something called public subnets or public subnet zone. And the idea of that is that the only reason why it's public is because it's directly attached to the internet gateway. The internet gateway allows internet traffic in as if you had a border edge router inside your VPC. So think of a public subnet as a DMZ or a demilitarized zone. Anything from the internet can touch it. So if you have ports open and if you don't have an additional firewall in place, your services can be accessed from the internet. Now hold on here. If you don't want, let's say you don't want any of your resources accessible to the from the internet, but you do need them to access the internet, as in getting updates, patches, additional configurations, and libraries that go with it. You want what's called a NAT gateway. Now, NAT gateways operate exactly how it sounds like, network address translation. And in fact, there's a special term for the NAT gateway we use. It's actually called port address translation in network engineering world, a source port address translation to be exact, where you have a single elastic IP, which is titled EIP inside AWS. Elastic IP is what is assigned as a static IP from their pool directly inside your VPC attached to a device such as a NAT gateway. This NAT gateway must live in the public subnet because the internet has to go to and from it as if it were a border edge router. So always remember that your NAT gateway, if you want public-based resources such as the internet, you must put it in a public subnet. Again, the only reason why it's called a public subnet is that the only difference between a public subnet and a private subnet is that the public subnet uses the route tables. So anything with 0.0.0.0/0 goes to the internet gateway route table rather than the route table of a private subnet going directly to the NAT gateway itself. And that has another route table. So anything for 0.0.0 that we have for the private subnet, it goes to the NAT gateway and does your egress request for you on your behalf without opening up ports to the web directly. Now, in this case, we have a private subnet, a single private subnet, and a single public subnet. Let's say we want people to access Amazon Web Services RDS, which is a managed MySQL equivalent or PostgreSQL equivalent as a database management engine. But you also don't want your AWS serverless functional code like AWS Lambda, for instance. You don't want it to have any form of ports open or access. It can only should be accessed directly by your database service. To do so, you put the private subnet with your AWS Lambda, anything that you don't want directly accessible from the internet. And then you want to set the route table directly to the NAT gateway you create. Now remember, from a cost standpoint, although Internet Gateway or IGW does not have a cost associated with it, NAT Gateway does. So if you have non-workloads that don't need ports open out to the internet, you use a NAT Gateway, but you do get charged for it, not only for your traffic going out, but also from your perspective of the amount of CPU hours being utilized against the NAT Gateway itself. So that's what we have so far, and it's a very basic concept until you get to additional architectures. Now, we spoke a little bit about route tables. Now, what do they mean? Think back to your network engineering concepts. The OSI model will operate at layer 3, right? We want to route traffic from to and from. We have the concept of IPv4 and IPv6 addresses. Now, just as remembrance here, we have the 10.0.0.0/16, which is an IPv4 address, and these 128-bit numbers that you see here that almost represent a MAC address looking format. That is an IPv6 address, and accordingly. There is no IPv5 version 5. There is just IP version 4 and IP version 6. The easiest way to remember how many bits are in an IP address, for instance, IP version 4 are in octets, right? Octets. Each of these 0 to 255 ranges times 4 is 32-bit. So IP version 4, 4 octets, 32-bit. On the other hand, IPv6 again is 128 bits. So 2 to 128, that's roughly 2 to 3 IP addresses for every square inch on the planet. Pretty amazing when you think about it, how far we've come. Now, from a route table perspective, you have to understand, regardless of your subnet, each subnet always has to have a route table. Just like you have in your own house, you have a route table to the internet. You have a route table for entry for your local network, which is the same as the subnet, potentially, if you're dual stack for IPv4 and IPv6. And eventually you have a route going for all other networks, 0000/0 for IPv4 at least. And you should always have the target to be an interface of another firewall or an interface IP address or for a gateway, such as NAT gateway, internet gateway. Remember that route tables, public route tables or public subnets, are directly attached to the internet gateway, and that means they are exposed to the internet. So stuff can connect to your firewall, stuff can connect to your DMZ or your services, so long as they're in the public subnet. Think of it as DMZ. And when you think of private subnet, remember that you don't have direct connectivity, regardless if you have a NAT gateway or not. So NAT gateways or private subnets, they go hand in hand, but you don't need them all the time. In this case, we have a specialized firewall appliance, let's say from Palo Alto, Checkpoint, or whatever other enterprise vendor that your firm or company may use. Your firewall appliance runs on an EC2 instance and will have multiple ENIs or Elastic Network Interface cards, the equivalent of NIC inside an on-premise server. You would have your route table from the public subnet hit this firewall and it'll forward it over, and the firewall's route table up here would actually go up to your internet gateway inside the public subnet. And so while you may still have other potential EC2 instances here running inside a public subnet, your firewall will shield and route traffic to and from the private subnet using its own route table on the private subnet, which the 000 will go into the interface of this inside interface of this network card for your firewall appliance. Your VPC has an implicit routing, right? You have implicit routing, route tables, so you don't need to build and worry about configurations of how it works and how does it scale. It scales for you. So this is actually infrastructure as a service to its finest. So it can scale up and scale down depending on your needs. You're rated at 1 gigabit per second by default. You can go upwards, and then depending on your burst of traffic requirements, you may need to contact AWS for a warm-up to scale out and scale back in if you're using such as a Elastic Load Balancer, for instance. And remember, VPCs mean Virtual Private Cloud for layer 3 networking. So if you were on-premise at some point utilizing network engineering as part of your career field, you might work with Cisco, or you might work with Juniper, network switches and routers and firewalls. And while you don't really have to worry about all of that inside the cloud, the networking is done for you. You just have to know how to route it and manage the actual administration piece rather than worry about the deployment and the scalability. So VPCs are highly powerful for what you need for many workload types and applications. Now we also have the concept of security groups and network ACLs. Now, you would think network ACLs and security groups are really the same thing, but they actually serve two different purposes. Network ACLs work at the network layer and are stateless. Right? Stateless means that you have to provide an allow or an explicit deny inbound as well as outbound for a complete connection, because you have a two-way connection for TCP especially. For security groups, it actually operates at the instance level. So think of security groups as a virtual firewall for each instance. And you only have allow statements. You can have egress allow, you can also have ingress allow, but there's always an implicit deny. Network ACLs are considered dumb. They don't have any statefulness to them. And you might be wondering, well, why do I need to use both then? Why can't I just use security groups? Well, think about network layers of security. Just like we have network layers of a stack, you want to have network layers of security. So in the event that there's a developer operator or a developer supporting engineer or a security analyst might accidentally set a security group incorrectly. They might allow 22 from the internet inbound, which is SSH, but you do not want that. If you accidentally misconfigure the security group, you also have an extra layer of security at the network ACL level to say that there's always going to be a deny inside from the internet to inbound ports of 3389 or even egress blocking it. So you want to think of security as layers of protection. Security groups always operate at the instance layer. Network ACLs operate at the route table VPC construct. Remember that VPCs are regional-based VPCs, and you can have all kinds of VPCs in your account per region, as long as they don't overlap, especially if you want to network with them. So think of this as other ways of having a firewall, a basic rudimentary layer 3 and layer 4 firewall right here at the host layer, and then a basic stateless firewall that doesn't track state. That means you have to have explicit denies and allows, ingress and egress. Now, when we say stateful versus stateless, let's have a quick concept of TCP again. Remember that TCP had a three-way handshake. Right? Three-way handshake. Okay, a three-way handshake includes the following at minimum, right? You have a SYN, which is a synchronization request. You have a response, SYN ACK, right? It has its response with a SYN and is also sending an ACK at the same time. And then finally, your client to your server has an acknowledgement to that other SYN. So sync for synchronization, ACK for acknowledgement. That three-way handshake has to come from somewhere. So if you initiate a three-way handshake from the security group outbound to the network address translation gateway, you only need to have, really, by default, security groups have allowance for everything, as well as egress allowance for network ACS. You could come in and go out to the internet and get a connection loop back around when you complete that connection, and you don't have to require, from a stateful standpoint, ingress allowance. Now, if you introduce the concept of a network ACL, you have to allow the source ports accordingly. So you have to allow something coming back to you from the source ports or ephemeral ports of the server side, such as 80 and all the way through 65,000 and some odd ports. And you also have to allow ports for the source port side on the ingress side here, potentially from the original connection state, anywhere from 1024 to 65,535. That's a mouthful, but don't worry too much about it. Just know that security groups, again, their main concept is instance level, network ACLs at the route and VPC level. Stateful means that you don't require explicit allow back, but stateless does mean you need explicit denies and allows because there's no implicit denies already. Again, we talked about a little bit about NAT gateways and internet gateways. Remember that the public subnet always has an attachment to an internet gateway. And remember that you make something public subnet by having a route table directly route everything 0000/0 to the internet gateway. That's the implicit route. Now, internet gateways always are required for traversal to and from the internet. And of course, internet gateways have an inbound and outbound to public subnets. NAT gateways, remember NAT gateways look like this, right? It has one way, look at the arrows, one way, going egress only. And again, that's source PAT, source port access translation. That's what we call it. Now, the horizontally scaled out and in when you need, based on your traffic load requirements, and you might need a AWS warm-up if you want to have a spike, especially when you have elastic load balancing services. So please keep that in mind. Now, IPv6 support, you saw those IPv6 addresses, but there's also a very special egress-only internet gateway meant for IPv6, and that's called the egress-only internet gateway. When you see egress-only internet gateway, think of IPv6. So while you can dual stack internally To go outbound, just like a NAT gateway for IPv4 would, egress-only internet gateway is meant to act as a NAT gateway for IPv6. Now that sounds really confusing, and it might be. Just think of NAT gateway serving the same function as egress-only gateways, but egress-only gateways are IPv6. NAT gateways serve the same purpose, egress-only IPv4. Don't ask me, that's how they named it. And remember that you can also dual stack, have support internally as well as egress outbound through these steps right here. You have an association of an IPv6 CIDR block, which you can do without any kind of egress gateway, and have inner traffic inside your VPC across availability zones, as long as the route support your scope of IPv6 subnets. You also have route tables that are accordingly required for local and traversals to the internet. And of course, you have to update your security group rules and change your instance types too. And you're wondering, well, why would I change my EC2 instance type? Well, only certain instances actually support IPv6 out of the box. So even if you have an Ubuntu Linux operating system, which you've been working with at the beginning of Linux Foundations potentially, or if you've been working with it in a different context from a different system, perhaps a Bastion host, you really have to understand that while the OS supports it, your actual hardware, which is the underlying virtualization piece of the VPC and EC2 services itself, there's only some instances that fully support the appropriate speeds of IPv6. And really, one example is m4.large, right? So you want to assign an IPv6 address to your instance, and obviously configure IPv6 on your instance locally as well if you're not using DHCP. Now, stop and think for a second. What is DHCP again? Give us some time. All right, if you have it, Dynamic Host Configuration Protocol, the thing that gives you automatic IP addresses as you join the network. Very important IPv6. Just look how complicated this looks versus IPv4. So please keep that in mind that you can always do a dual stack whenever you need to. Native support inside AWS egress-only gateways and already built into your security groups and VPCs. Now, DHCP and DNS support are also hand in hand together. You always want to have both enabled whenever possible, unless you have a really good reason not to. Remember, everything in the web is designed around simplicity, utilizing fully qualified domain names. So if you went to www.aws.com for whatever reason, you don't need to know the IP address, you just need to know the domain name. That is resolved using domain name service, and so you want DNS resolution whenever possible. Now, DNS resolution inbound is different from outbound. Whenever your computer goes to www.google.com, for instance, it has to do a DNS resolving to your ISP from your router. Say, where is google.com? Send me the IP address. Same thing happens locally on your network. One of the most important things is whenever you have a VPC, edit your DHCP options set, edit your DNS resolution and DNS host names, and allow for the automatic configuration of your VPCs to have both enabled whenever possible. You never want to have a service that is focused around the cloud or anything that has a workload that you need to connect to without an IP address. It won't happen. So remember to enable these whenever possible and check them. And obviously, you might see here highlighted create flow logs. That's just another way of saying, hey, I need to create logs based on the connections going to and from somewhere, whether they were allowed or denied, similar to firewall rules, only you're only seeing the original connectivity itself. Remember that you want DNS resolution, DNS host names, and DHCP automatically enabled whenever possible as a best practice, unless you have a different need or use case reason to have IP addresses only. Now let's take a quick break. Think about what you learned previously in different network classes, the OSI model, and how you can apply on-premise concepts back into the AWS VPC and what that would take from using ACLs that you would use as a firewall internally, and what is it called and what does it look like inside your AWS account itself. We'll see you then. Okay, welcome back from break. Let's talk about endpoint and site to VPC connectivity options. Now, VPC endpoints are a little bit different. Now, this is a very interesting concept that most newcomers come to AWS going, well, doesn't everything come into internal networking and traffic? No. Actually, you get billed for everything going egress outside of your account and in between availability zones and between different regions. And the fact is, if you use a different AWS service, let's say you're using AWS Glue in this case, or and you want to talk to Amazon S3, which is for storage, it actually goes out to the internet and loops back around to the endpoint. And you're getting charged for each of those connections. You might be wondering, well, why didn't AWS design this to be internal only to begin with, and why am I being charged with it? Great question, but remember that AWS is always about flexibility. It's not always about security only. So if you need the flexibility of going out and back in, that's what's by default, unless you create something called endpoints. Now, a VPC endpoint is also a chargeable feature, but if you do enough traffic, right, enough traffic at scale, you might find it being cheaper than going out and paying internet and round robin pricing for that internet and traversal backend. You could just go to the VPC endpoint, and then you're not charged for the actual network connectivity and traffic being transferred internally, at least within the same availability zone and the same region. Now, you also have to understand that VPC endpoints, if you don't push a lot of traffic, they still cost a certain amount of money each month. Check the white papers and VPC endpoint documentation for more information. Now, you have to understand that VPC endpoints are just another way of saying, hey, I have an API and I have a certain API at a different IP address or at a gateway for different connections. Amazon S3 is one for gateway requirements, and so you would actually put a route table entry as your VPC endpoint inside your router for your VPC subnet. And so whenever it does a query to S3, it routes directly to those endpoints internally, and you're not being traversing the internet and being called out accordingly. Now, there are other benefits besides cost. There's benefit for security and compliance requirements. So, for instance, if you have a highly secure environment, you have compliance regulations saying you may not traverse the internet, VPC endpoints are impossible for you to say, hey, I'm not leaving my VPC whatsoever. It's staying inbound on the AWS network and never traversing my internet gateway whatsoever, right? So remember that, think of VPC endpoints as private API connections either by IP address or by gateway via route table itself. It used to be called AWS Private Link. We've recently converged on VPC endpoints instead. Private links is another way of saying I'm creating VPC endpoints for an API, for instance, and I want to provide that access directly to another VPC, another account that could be maybe a customer or a partner. They will utilize the private link IP address to actually traverse traffic and figure out and interact with your API itself. Pretty cool how you can actually offer these things as a multiple level service provider, a partner, or even directly to customers with a very specific use case in mind. Now, let's take a quick pause and figure out, well, we've been talking about networking all this time. What about software development kits? AWS command line interface, CLI, and the web console itself. Well, they all look a little bit different, and they all actually don't ever connect to your VPC. And if you're wondering why I'm talking about SDKs, the CLI, and the web console, and a network-focused VPC in slide deck, well, it's because of this. We want to make that distinction that you are not connecting to the VPC. You're actually connecting to APIs that actually interact with your VPC. Now, there's a difference. SDKs are for programming language construct. So what I have here is an example of the Boto 3 library for Python that will interact and create a connection, client connection to S3 directly. Now, is S3 inside a VPC? Pause, think about it, get back. Okay, hopefully you have an answer. The answer is actually no. Your S3 is a regional construct, not a VPC construct. You can create your S3 bucket inside US East 2 like Ohio, and it's going to be available in the Ohio region. Although the names itself have to be globally unique, you're actually not interacting with anything in the VPC. There's no IP address unless you do a VPC endpoint. And in fact, there's no EC2 anything. S3 is not part of an EC2 service. So remember that VPCs are an EC2 service. S3 is not. It's a completely different service altogether. And so it's completely decoupled, and you're not connecting to the network. You might be connecting to a service that may interact with other assets in your network, but you're actually not connecting to the network. The same goes for the AWS CLI. You interact with things that could be part of your network, but you're not connecting to the network itself. For instance, I can't specify a connectivity pattern directly to my VPC for 10.0.0.0/8. The same thing goes for the web console. I may be manipulating things in the VPC, but I'm not connecting to the network. The only real exception to this is the console might be opening up a EC2 instance session management session, which allows you to connect to your EC2 instances inside your network. But you're not actually connecting to the network. You're connecting to a very specific remote desktop or remote terminal of your instance itself. And that is specialized software. Similar to what you do with LogMeIn or the help desk related tool sets like TeamViewer, for instance. You are still traversing the network, but you're accessing that one endpoint, that one instance, okay? So this is a very common misconception. SDKs, CLI, and consoles, they don't access the VPC. You need different technologies for those. However, these are some great technologies that you need to use when you're creating your workloads inside AWS. Now back to virtual private environments, we have virtual private networks. You might have seen virtual private networks or VPNs as a consumer. If you use specialized software and have a username and password and maybe a certificate of authentication, you connect to someone else's virtual private network from a paid service, and perhaps you can access sites that you normally block at the United States level or another regional level. Perhaps you wanted to make sure that it's encrypted using IPsec tunnels or SSL VPNs, and you want to make sure that no one's snooping on your traffic to and from between you and the website itself. That is a VPN at the client level, right? Client singular, which means you are trying to connect to a larger network, and it's just you and you alone, just me. Now, VPNs are supported at the client level, and they're also supported at the site-to-site level. But let's talk about client real quick. You have your host that you install software on. There's a managed client VPN endpoint that is configured to connect directly to your VPC. So if I have 10.0.0.0/something and I have a 10 address, and I connect to the 172.31 address up here that you see right here, I can't do that without a virtual private connection, right? I can't use it without VPN services. So you can actually pay for the client managed VPN endpoint services within AWS, use specialized software, and actually underneath the hood that uses OpenVPN protocol and supports 443 and 1194 over TCP and UDP egress. Okay, so if you wanted to connect to your VPC from the airport, for instance, as long as 443 and 1194 are open and support the OpenVPN protocol without blocking you, for instance, you can connect to your VPC network and ping your own EC2 instance if you want. Now, that doesn't sound very exciting, but that's actually a really amazing thing to do. You're extending your workload network to anywhere else in the world, or perhaps your own single mobile device that you're looking to interact with a particular service for. Now, VPNs are also the point of site to sites. So you use what's called an IPsec VPN in most cases. Most client VPNs don't utilize IPsec, although they could. Most of the time, you'll see OpenVPN or SSL/TLS in use. In a site-to-site tunnel, most of the time you have IPsec VPNs utilizing those tunnels instead. And there's two phases of them in an internet key exchange. You can look up more about those in the future. But remember, internet key exchange always operates on UDP 500 by default. And when you're talking about site-to-site, you're saying two larger networks, more than one computer on each side want to connect to each other. Okay? So you are a network or a data center, you want to use site-to-site. You're basically saying multiple clients, you need to be able to connect to multiple subnets, and vice versa, depending on your trust relationships. Okay? That's a site-to-site tunnel. You can use VPN connectivity for that. But wait, there's more. Direct Connect is a completely different option altogether. So if you've been in network engineering in part of your previous roles, you might have connected two data centers together using an ISP over a wide area network. For that, you also make sure you have to use border gateway protocol, and you need to call your internet service provider, and they need to provide multiple links and setups criteria, and you have to provide the route between the two. Lots of setup, lots of configuration. Well, the same premise is with AWS Direct Connect. You can actually operate directly with AWS itself or at the partner level, which offers different speeds and different steppings and integrations. Right? You have 1 gigabit per second, you have 10 gigabits per second upward, and these are direct dedicated connections. Dedicated connections. So if you took an Ethernet cable, perhaps one that you might buy on Amazon, and extended that cable, assuming that there was no signal degradation from my house to your house, right? How long will that be? That's a direct connection, right? I'm extending my network to yours at layer 2, right? At layer 2, that is the switching to be done. Hence, layer 2 VLANs right here. Now, you can go through the partner, or you can go through Amazon Web Services cages directly. Now you have a dedicated connection that is faster and more reliable. And the best practice is usually to have a VPN backup, which can scale up and scale down and vary in latency depending on the internet backbone and how you're routing to that. A direct connection is a logical connection from one point of presence to another to Amazon Web Services as if they were your data center, just extended. So just think about direct connection as BGP, private line, layer 2, and logically extending your network at that layer. Now, there are also VPC to VPC options. So you don't have to always be on premise. Let's say you're native in the AWS Cloud already and you have multiple accounts, multiple networks. How do you connect them all together if you had to? Well, we have another set of options for you. We have something called VPC peering. Now, a peering of a connection is not a VPN. Again, that's a repeating, not VPN. VPC peering means you have a direct connection logically, internally, never traversing outside of Amazon from one network to another, one account to another, one region to another. So remember that a direct peer-to-peer connection at the VPC layer. We have a 10/, and we have a 172.31/, and we have VPC-A and VPC-B. Notice that they are non-overlapping subnets, right? Non-overlapping. They must all be non-overlapping. The other thing to note is that VPC peering is not transitive. So if you connect VPC-A and B together, VPC-B cannot traverse VPC-A and connect to VPC-C. Right? You have to have another connection directly as a peer VPC-B and VPC-C. And all those route tables have to be updated. So if you just have two VPCs being paired together, A and B in this case, you have to update the route, saying anything going to 10.0/8 goes to the connection here, rather than being dumped off or sent out to the wild internet. Again, VPC peering is a direct connection between VPCs, requires route table adjustments, can be cross-region and cross-account, but they're non-transitive, okay? So you have to have a dedicated peering connection on each one. What happens when you need to scale? Well, for that, we have Transit Gateway. Transit Gateway is a way to tell you to say, we need multiple VPCs to interact with one another. A to B, for instance, right here, A to B. Oops, and let's try to get that pin going one last time. There we go. Let's say A to B, and we also need them to connect to, over here and over here. These two connect to each other. That's a lot of connections when you think about it. Whether it's on-premise or using VMware in the cloud with an attachment, an extension of your data center, Transit Gateway is really your option. It is a hub. It helps you manage multiple VPCs and multiple networks together in one solution, and you can attach it to that hub. And it's also abbreviated Transit Gateway with TGW. You can have VPNs, direct connects, or direct VPC attachments between VPCs for workloads in the cloud. So think of Transit Gateways as helping you achieve multiple network connectivities for complex routing patterns in a central location, and supports intra-VPC routing without having to create a peer for many, many different things. You can accept multiple connections, and it's a great way of saying, I have a hub and spoke model with the multiple accounts. So let's say we can have all this as an account 1, all this is an account 2, and we can have, let's say this one focuses on security, this one focuses on prod. That is the best practice. So when you think of Transit Gateway, think of hub and spoke, everything centralized. All right, let's take a break and get to our demo. Sure. Welcome back from your break. I hope it was a good one. Let's get started on VPC network connectivity. Notice I'm in the console. I'm not connecting to a network. I'm in the US East 2 Ohio region, and I'm going to use the launch VPC wizard in this case. I want a public and private subnet, and it's telling me it's going to create 2/24s, public subnet that has a NAT gateway built in, an internet gateway attached, as well as a private subnet that has a route table directly to the NAT gateway. Let's see what that looks like. Let's use a 1010. I'm going to say my VPC name is demo VPC. I'm going to use a single availability zone. I can also use a different availability zone if I wish. It just gets charged a little bit more money. I'm going to say 1010 here because these are /16s. I want to narrow it down to a /24. And we have, and just because you call it a private subnet doesn't mean it's a private subnet. It's just a way of saying, hey, I went ahead and I'm going to associate route tables to a NAT gateway for you. Now it's saying I don't have any elastic IPs, so what I'll go ahead and do is go ahead and type in VPC here. I'm going to right click, create a new tab, so I don't exit from that screen there. I'll grab an elastic IP, which remember that this gets charged even with your NAT gateway. I'll say that's best practice tag, so Fullstack demo. I'll say Fullstack lab, and then I'll say VPC demo. I'll grab an IPv4 address, elastic IP range. Do not use the global static address accelerator. That is actually a way to have multiple cross-region backbones using very, very speedy and expedited quality of service between your networks for global needs. So don't do that. Not yet, at least. All right, we have a public IP assigned to us, which is 18 ending in 252. We get charged per the hour for that, unless it's attached, and then you get to attach and charged at the NAT gateway level. My first NAT IP, I can name it whatever I want, which is the same as saying the name tag down here. Okay, we'll go ahead and refresh here, and now it has an elastic IP right here, EIP. I don't need a service endpoint, but I can always create one if I want. DynamoDB supports one, S3 supports one at the gateway levels, and I can go ahead and do that, but I don't want to. You can certainly experiment with that as you wish. We're going to close that, enable DNS hostname, and do not change the default hardware tenancy. If you go to dedicated hardware tenancy, you're actually reserving an entire server inside of a rack to yourself. You don't want to be charged for that. Go ahead and say default, check your settings one last time, create VPC, and watch the magic happen. And as it goes, you might see this take a little bit, and the elastic IP, public IP, has to be attached to creating route tables and putting this all in. You can do this manually if you wish for an extra challenge. Just work backwards. Remember what you need from a VPC: internet gateway, NAT gateway, public subnet, private subnet, and then the route tables that point to each. This will take a few minutes, so as we go through that, we can also do this. We can also look at different aspects of another VPC. By default, you should always have a VPC that you create, and I call mine default, and that's the one that comes with your account, usually in a 172.31.16. And of course, you have nothing in here. But if you go to your subnets, it has 3 different subnets for you by default. And notice that despite the /20s, there's a few IPv4 addresses missing, as well as the /24. That's because Amazon Web Services will take up to 3 IP addresses for different internal needs, such as broadcast, gateway, internalized routing. So always account for that extra lapse in IP addresses. Always -3 at a minimum, but I like to do a -5 for my realistic IP address set. Now also notice that you can also do flow logs if you wish, but also each subnet is associated with a route table. And route table says, hey, everything internally going to 172.31.00.16, want that routing locally internally. That's all there is to it. I can also edit the association, and anything going to 0000 goes to my internet gateway. And because it goes to an internet gateway, I know that means that's a public IP address or a public subnet rather than a NAT gateway itself. Now, for an easier view, or perhaps a less easy view, you should always go to the route tables themselves and see. This is my main route table, which is the default if I don't have an explicit subnet association. Notice I don't have explicit association. So by default, all of these will use my main public route table. Why is it public again? Because it connects directly to an internet gateway, not a NAT gateway. So I have to explicitly pair these with the associations. But you saw an association last time. That's because the association is implicit because there is no explicit association. And there is no other route table. However, as we create our VPC, demo VPC here, it's still being created. I can launch things now, which is awesome. And my demo VPC here, now it has my 16 associated with it with 10.10.0.0.16 non-overlapping. So technically I could peer the two. I have my subnets, a public subnet, which was called, and a private subnet. And I can also filter by VPC or sort it by VPC. So I like to name mine. I have mine default. Yours won't see like that unless you named it. I have a public subnet. Again, the route table accordingly goes to an internet gateway. And a private subnet goes to a NAT gateway, right? Your NAT gateway instead. What does that route actually look like inside here? Well, you have a network ACL if you wish. Again, inbound rules, we have outbound ones, and they have to be explicit. By default, all of them are inbound and outbound allowed. Route tables, they can have names, but remember we don't have a main one. Main means by the default route table, and that is not default. We have subnet associations explicit to the public subnet for this one, and that means we have a unexplicit one by default, saying go to the another one, which was, let's check it here, a private. So we want all of our default routes to be in a private subnet association for security purposes. That's a good way to make sure that you have security, never the reverse. Why? Well, because NAT gateways don't have open ports to the internet. So if you accidentally put something in the wrong subnet, make sure your route table is point to the private subnet, the best security possible. Again, network ACLs are wide open by default. So you want to do increment rule numbers as necessary. And implicit and explicit rules do apply. So you have an implicit deny already, which is a star here. But you have to do explicit denies or allows for different traffic to come in. Remember, you have the idea of ephemeral ports. So even if you have a service port of 80 and 443, you might have source ports needing to be returned with inbound, which is anywhere from 1024 to 65,535. How did I come up with that number? Look up 2 to the 32nd. Actually, look up 2 to the 16th. I'm sorry, 2 to the 16th, and you'll get 65,535 ports as usable. Port 0 not being counted. Okay, security groups are also default as well, and they have all inbound and all outbound by default. Now, when you create an EC2 instance, we'll go to EC2 here, and you can certainly launch an EC2 instance inside a public subnet for connectivity purposes. So I'll go ahead and launch these. I'll use my defaults. And notice I can have it go to my demo VPC, and I can launch it in the public or private subnet. If I want egress only traffic to the internet with the way it's configured, private subnet. If I want the internet to hit it, in case it's a web server, public subnet. That's all there is to it. The public subnet, I want to have a public IP address because I want the internet to hit it. Assign my roles if necessary. So I can always say I need but I want to be able to connect to it using SSM instead. Well, what does the SSM user data agent look like? Well, let's look it up real quick. AWS EC2 user data SSM agent installation. Now, user data means I want to install the SSM agent, session management agent, where I don't actually need ports open from the web. I can just connect directly from my AWS console into my instance. So because I'm using an AMI of Amazon Linux 2, and it's using, looks like a Red Hat and CentOS version, I'm going to have that as part of my startup bootstrap script. I'm going to use a role that was already created. And if you're wondering what that role looks like, you'll learn more about roles in a different module. But To show you what a role looks like, a role is the permissions that you have for a very specific requirement for different AWS services. So I have my VPC lab SSM EC2 instance role, and it's saying I can allow SSM managed instant core and patch association in there. All right, those are the policies that give me that permission to one or more APIs. If you want to see what that policy looks like, that's what it is. Just a very, very specific access control list to IAM. IAM being Internet Authentication Management. Set my role. I want it in the private subnet instead because I don't need it to be accessed from the internet for whatever reason, but I do want it to access the internet. And I don't want a public IP address, so I'll say use the default of disable. And then I will also put in the user data, which only runs once on boot, and only that one time. So make sure you have everything right. I have the role, or we can talk back out internally to AWS without opening up ports. Notice again, 251 IP addresses available, not the 254 that you were expecting. This looks pretty good. Let's add storage. We'll have an EBS instance. Encryption, always use the AWS EBS default keys. So you don't get extra charges on KMS. You can add tags when you want. Again, best practices is always add a tag when it's volatile. So I'll use Fullstack Lab. I'll use demo for whatever reason. Added security group. Well, technically, I should allow 22 for SSH open from my IP address, and then this is at the time of my local wide area network IP address, but I actually don't need one. So I can utilize this default, but I'll create one. I'll create no traffic inbound. I'll make that my description as well. So basically, I'm removing this rule from allows, and it's going to give me this warning saying, hey, you need the port open. No, I don't. You'll see why, because we're using SSM agent, which actually calls out to its own Amazon Web Service internal version of remote connection. It's going to be pretty cool. Just watch. I'm going to acknowledge that I'll use whatever key pair I want, and I won't be able to connect to it for whatever reason. It's going to launch the instance. I'm going to name the instance whatever I want. So demo VPC SM. Now, again, even though I'm launching an instance inside my VPC, I'm not connecting to the 10.10.something network. It already gave me a DHCP address, which is awesome. It's running already. We'll close the original support ticket here, and we'll try to connect to it. And it's still running here, and we'll see if it connects to it properly. Now, there's different methods. The session manager is where you can connect to it internally and still doing initialization and status checks. Usually you want to wait till status check 2 of 2 is complete before you want to try to connect. We'll refresh one more time, and if it doesn't, we'll wait for that to populate accordingly. Looks like it's trying to load the agent right now using the internet. Remember, it has to egress out to the internet using NAT gateway. How does that work? Well, let's go back to your VPC just to double check on that. VPC, open it up in a new tab. And as you can see, inside our demo VPC, we have 2 subnets. We have a public and a private. Our private subnet has a route table saying everything going to the internet go through your NAT gateway. Your NAT gateway must sit inside a public subnet. It has an elastic IP, and it's actually sitting inside public subnet with a 10.10.0/24. And we look at my public subnet again, back in here, 10.10.0/24. So let's go back to this guy and see if it's actually up and running. 2 of 2 checks passed. That's a good sign. We'll go ahead and connect. And it has back the allowance of connection. That means the EC2 instance is directly talking egress only to a very special Amazon Web Service session manager endpoint. And so I don't have a public IP address. I don't have any open ports based on my network ACL, even though it allows everything. If I look at my security group here, which is at the firewall instance level, I said no traffic inbound. Okay, and I can actually verify this going back to my VPC and saying, what is this attached to it? Well, I have these levels of information here, the key pair and other stuff. So security here, which is my IAM role, and security group, no traffic inbound, Again, no inbound rules, already implicit deny. That's how we know it worked, and it went out to the internet via NAT gateway. Let's go back to our EC2 running instances here. And let's do a reverse connection. So it's kind of like connecting to LogMeIn or TeamViewer. Connect, no open ports whatsoever, and it should give me a terminal window directly to the instance. LS here. Wow, that's a lot of information. We'll clear that. I'm going to try to zoom in, and it looks like it won't let me zoom in here, but bear with me that I can go who am I, which is EC2 user or SSM agent user. I can ping google.com, ironically coming from Amazon Web Services, and know that I can get out to the internet. So that's all there is for this lab. To actually clean up, if you've been following along, terminate your connection here. You want to make sure your instances are destroyed. So go ahead and terminate your instance. Wait for that. And because you didn't create anything else, you can actually go to your VPC when that's finished terminating and actually terminate your VPC and also delete your NAT, which will also delete your NAT gateway. But you'll also have to disassociate and remove your and see that the instances is still running at this time. It's shutting down. Let's give it a little bit longer. Remember that you're asking to provision something on demand in the cloud, something that is longer for an actual place. We have a terminated instance completely. So let's give that another shot. Terminate or delete VPC. And it's saying unable to delete. We have another one. So let's go ahead and make sure we have disassociate our NAT gateway first. So delete. All right, so that's being deleted, and actually it's going to release that public Elastic IP address back into our pool here that we own or that we've captured. So we can actually disassociate. It's probably going to be an error because it's still deleting the NAT gateway. You'll have to wait for the NAT gateway to be completely terminated in here and disassociate it with first, and then followed by your VPC, and then your Elastic IP address needs to be fully released. So that is still what's going on here. I'm going to pause the video really quickly and wait for this to occur. We'll finish out the cleanup so you can return back to your labs. All right, so we're returning back from there. Our VPC is still available. We have a NAT gateway that's finally fully deleted. Let's go to our Elastic IPs, refresh, and see if we can disassociate that. Release the IP address. Cool. Make sure that's disassociated. We'll disassociate our internet gateway that was created with demo VPC, as you can see right here. Detach from VPC. And then we can also delete it. We'll delete it in here. And then we'll also delete the VPC finally for our remaining items, which will also take care of our security groups. We'll delete the public and private subnet, the route tables, and the security group we created. Yes, we want to do that. Delete. And you are finally cleaned up. Thanks for joining us. Good luck in your labs today.